All right. What we're going to be doing next in the unit is we're going to take the information that we've already been finding and we're going to use it to sketch a curve without a calculator. So to title these notes, I'm just going to write curve sketching. And before we get too deep into it, we're going to go ahead and just look at a problem that has given us the information, and then we'll just draw that information first. And then we'll do an example where we're like finding all the information ourselves. So we're going to sketch the graph that satisfies the following conditions. So f of 0 is 0, f of 2 is 3, f of 4 is 6, f prime of 0 is 0, f prime of 4 is 0, f prime of x is greater than 0 on 0, 4, f prime of x is less than 0 on negative infinity, 0, and 4 infinity. And then f double prime of x is greater than 0 from negative infinity to 2. F double prime of x is less than 0 from 2 to infinity. All right, so if you did this on notebook paper, maybe draw your sketch on graph paper. We're definitely going to need some graph paper over the next few days. I have these handy little graph sticky notes that I'm going to use. Okay, so when I do these, I always start off just by drawing the exact points they gave me. So we have the point 0, 0, 2, 3, and 4, 6. Okay, and then they tell us that the graph is increasing from 0 to 4, and it is decreasing from negative infinity to 0 and from 4 to infinity. So this is where it's increasing, it's slanted up. This is where it's decreasing, it is slanted down. They tell us that at 0 and 4 we have a slope of 0, and so that means that those are our maximums and minimums. And then it tells us from negative infinity to 2 we are concave up, and from 2 to infinity we are concave down. Okay, so from negative infinity to 2 is concave up. From negative infinity to 0 is decreasing, then 0 to 4 is increasing. So I'm going to say decreasing to 0, and you can see that I'm drawing that so that it fits the concave up. And then increasing from 0 to 2 for sure, so I still have that as concave up. And then it's increasing still from 2 to 4, but it's now concave down. So now I'm going to make it look like this. And you can see that I've done the part where it has a slope of 0 at 0, and I'm kind of making a maximum at 4, so I'm making it have a slope of 0 there as well. So now I just need to do concave down from 2 to infinity and make sure, I already did from 2 to 4 is concave down, but from 4 to infinity I need it to be decreasing, so we're keeping it concave down and we're making it decrease. So all the pieces kind of work together. You might have an idea of like, yeah, these all needed to be going up because from 0 to 4 goes up, but the shape of the curve is determined by the fact that it's concave up or concave down. So that definitely benefited me there. Okay, so when we are actually looking at our curve sketching problems, there are things that we need to think about. There are things that we need to actually check and write down information for. Okay, so 2 things to think about. One is the domain of the graph. and the other is symmetry of the graph. So if you know a graph has symmetry and you draw one side of it, then that can help you draw the other side. So that's definitely something to keep in mind. All right, things that we are always going to check for when we know that we are sketching a curve. We're going to check for intercepts. Definitely the y-intercept, because our functions are in terms of x, and so you can plug in an x value and get your y value. So definitely y. X, if it's easy to solve. So if you have something where you can take the original function and set it equal to 0 and solve for x and do that relatively easily, then you'll do it. If the original function is something you do not know how to solve, then you don't have to sweat it. You can do the problem without it. Right? Another thing we always want to check for is asymptotes. So this is for our rational functions. So we are looking for vertical asymptotes, horizontal asymptotes, slant asymptotes. We want to look for where the graph is increasing and decreasing, and we want to look for the extrema. So I'm talking about the maxes and mins. And if you guys recall, we get these from the first derivative. We want to look at the concavity of the graph, and we want the points of inflection, and that's from the second derivative. So basically, anytime we're sketching a curve, we're going to walk ourselves through all of these steps. We're going to keep in mind the domain and the symmetry, and then once we have all of that information, we're going to go ahead and graph everything that we have. All right, so when we do this, sometimes, and I've been making you guys do it anyway with extrema and point of inflection, when you are answering questions and you're just saying where they are, you can typically just say the x coordinates, but I've been making you find the y coordinates because all along I knew that we were going to be graphing them. And so it's nice when you have intercepts that you can graph, but it's also nice when you have found your extrema and your point of inflection if those are written as points as well, because it just gives you more points to graph to sketch your curve. Okay, so we're gonna have points for intercepts, but also points for extrema and points for point of inflection, and that's going to help us make our graphs easier to draw. Okay, so we're going to start off with a rational function because these are pretty interesting to draw. And we're going to walk ourselves through all of these steps. So the graph that we're going to do is y equals 2x squared over x squared minus 1. And when I work with rational functions, I'm always going to factor the numerator and the denominator to see what x-intercepts and y-intercepts I can get and to see what asymptotes I can find. And so if I factor this, that gives me 2x squared on top because that's not factorable. But on the bottom, I have x plus 1, x minus 1 because that's difference of squares. So if I work my way through this, my y-intercept I'll go ahead and find first. I get that by plugging 0 in for x. So if I plug 0 in on the top, that equals 0. If I plug 0 in on the bottom, that equals negative 1. 0 divided by negative 1 is still 0. For the x-intercept, I'm going to go ahead and take that fraction and set it equal to 0. And so if I'm making a fraction equal 0, I really only need the top to equal 0. And so that means that 2x squared equals 0. And if I solve that for x, I'm going to find that that equals 0 as well. So the x-intercept and the y-intercept are the same point, which for this problem definitely makes sense. So vertical asymptotes, when we're looking for those, we can see what factors in the denominator equal 0. So I have a vertical asymptote at negative 1 and positive 1. Horizontal asymptotes, if you look, you can do limits if you want. So look as at the limit as x goes to positive infinity, that limit as x goes to negative infinity. And so when I look at this, positive and negative infinity would both do the same thing since we have x squared. And so the limit would be 2. So that means our horizontal asymptote is 2. Slant asymptote is none. I don't know if you guys remember this from rational graphs, but they either have a horizontal asymptote or a slant asymptote. They do not have both. So since we have a horizontal, we do not have a slant. So at this point, I'm done with everything I can find from the original equation. Now I'm looking at the first derivative. So I'm going to go ahead and say I'm done with the original. First derivative, y prime would be low d high minus high d low divided by low squared. And so that is 4x to the third minus 4x minus 4x to the third. And on the bottom, I'm going to go ahead and write this in the factored form. So x plus 1, x minus 1, those are squared. So y prime is negative 4x divided by x plus 1, x minus 1 squared. And so our critical points would be where the top equals 0, so that's where the slope is 0, or where the bottom equals 0, which is where the slope is undefined. And so for the top, we have x equals 0. For the bottom, x equals negative 1, x equals positive 1. And so I'll go ahead and draw my sign chart. So on the bottom, since everything is being squared, I know that the bottom is always going to be positive. So that kind of helps me when I'm plugging these things in. So I've got something over a positive on the bottom. Negative 4 times negative 2 is positive. Positive on the bottom. Negative 4 times negative 1/2 is positive. Positive on the bottom. Negative 4 times positive 1/2 is negative. And then negative 4 times 2 is negative. Okay, so this graph is increasing from negative infinity to negative 1, and then from negative 1 to 0. It is decreasing from 0 to 1 and 1 to infinity. There is a relative max. We switch from increasing to decreasing, so it goes up and comes down. There's a relative max at an x-coordinate of 0. We never switch from decreasing to increasing, so there is no relative min. And then if I want to find the y-coordinate of my relative max, I just need to go back to the original function and plug in 0, and we've already done that. That's just the point 0, 0. We already know that that's on the graph. Okay, so that's all the stuff we can find from the first derivative. Now for the second derivative, I'm going to go ahead and I'm going to take the negative 4x, and to avoid doing the quotient rule, I want to say that I'm trying to remember from last year. I think typically at this point I often avoided the quotient rule by just taking the bottom up to the top. So I'm going to write this as negative 4x times x squared minus 1 to the negative 2. These problems are fairly common, so it's pretty common to have something on top over parentheses on the bottom that are being squared like that. So what I did is I was thinking about the top being simplified, but on the bottom, instead of making that a product rule like that, writing it in its factored form, I just went ahead and I thought of the denominator like this, and I brought it up to the top and wrote it with a negative exponent. And I did that to avoid the quotient rule. And I think you can probably do the quotient rule. It's just this is how I did it on my notes. So apparently a year ago I thought this was a good idea. Okay, so my second derivative is the first times the derivative of the second plus the second times the derivative of the first. Okay, so if I clean this up a little bit, I've got negative 4x times negative 2 is 8x. 8x times 2x is 16x squared over x squared minus 1 to the third. It's plus, but it's multiplied by a negative. I'll go ahead and just say plus. Negative 4 over x squared minus 1 squared. So for me to be able to find where the second derivative either equals 0 or is undefined, I'm going to have to make these together, right? So I can have one fraction and set the top equal to 0 and set the bottom equal to 0. So I'm going to go ahead and get a common denominator by multiplying this by x squared minus 1 over x squared minus 1. And so I've got 16x squared minus 4x squared plus 4 over that common denominator. And so that's 12x squared plus 4. Okay, so if I think about the top, setting the top equal to 0, I'll go ahead and write this off to the side. 12x squared plus 4 equals 0. I would minus the 4 over. 12x squared equals negative 4. I would divide the 12 over. X squared equals negative 4 over 12, which is negative 1/3. And then I'd be square rooting a negative. And so the top is never going to equal 0. So that means our critical numbers are only from the bottom. And we've looked at this already, and we know that the bottom factors to be difference of squares. So this would be x plus 1 and x minus 1 to the third power. All right, so what I'm going to do is I'm just going to go ahead and do my sign chart using negative 1 and positive 1. And I'm running out of space. I'm trying really hard not to grab another sheet of paper. All right, so sign chart, negative 1, positive 1. So I'm going to use negative 2 and 0 and 2. And this time, whatever I plug in on the top is always going to be positive because I have 12 times whatever number I plug in squared. And so I know if I plug in negative 2, I'm going to have a positive on the top. On the bottom, negative 2 minus 1 is negative 1. Negative 2 minus 1 is negative 3. So negative 1 times negative 3 is a positive to the third. So that's going to be positive. 0 on the top is going to be positive. 0 on the bottom is going to be 1 times negative 1, which is negative 1 to the third. So that's negative. And then for the last one, 2 on the top is positive. On the bottom, 2 plus 1 is 3. 2 minus 1 is 1. That's going to be positive on the bottom. Okay, so this graph is concave up from negative infinity to negative 1 and 1 to infinity. And it is concave down from negative 1 to 1. And it appears that we have points of inflection at negative 1 and positive 1, but those cannot be actual points because negative 1 and positive 1 were where those vertical asymptotes were. So we're going to say none, and that's because of the vertical asymptotes. So the inflection does change, right? Concave up to concave down, it does change, but it doesn't change at a specific point. It changes at the asymptote. Okay, so we have all that information. At this point, we're going to go ahead and graph things one by one. So I'm going to get out my little sticky note grid to put on my notes. And I typically start off with the real points that are there because they're easiest to graph. Asymptotes are going to be pretty easy to graph as well. So y-intercept, x-intercept, that's 0. Vertical asymptote at -1. And +1. Horizontal asymptote at 2. Okay, no slant asymptote. So I took care of all the stuff that was for the original function, and you could, if you want, check it off as you use it. Relative max is 0, 0. So if it's a relative max there, then I know it's a high point. So the graph probably looks something like that right there. Relative min, there's none. I can see that the graph is increasing from -infinity to -1, and so that means that if I was to draw this from -infinity to -1, I'm not going to be able to use this side of the asymptotes. I would have to use that side, because this side of the asymptotes would be decreasing, this side of the asymptotes would be increasing. And if I look at the information I got from the concavity, then I can see that it's concave up from -infinity to -1 as well. So that's kind of interesting. So we can go ahead and draw that. If you want to have some more accurate points for this part, then you could go ahead and plug in to the original function like -2 and -3 just to see what's happening. For right now, I'm okay with this, just drawing that curve in. So it's going to look something like this. It's also increasing from -1 to 0. So that means that, and we already knew that, it can't be going down right here and following the asymptote. It has to go from -1 to 0. It's increasing. It's decreasing from 0 to 1, which we kind of already knew since that was a maximum. It's decreasing from 1 to infinity, which would have to be this side of the asymptote. If it was the other side, then it wouldn't be decreasing, it would be increasing. And then if we look at our concavity, that just supports it. So it's concave up from -infinity to -1 and from 1 to infinity. So we can see concave up and concave up. It's concave down from -1 to +1. So we just drew an entire rational graph without getting out our calculators, which I think is kind of cool.